Welcome back, Physics 17 students. I hope you all got the grade you wanted on exam 3. We're starting a new part of this course, beginning with this lecture. It deals with light, otherwise known as an electromagnetic disturbance or wave. I show a wave with a wavelength lambda. An electromagnetic wave is set in motion by the oscillation of an electric charge. Never mind why that is true. The frequency of oscillation of the electric charge is symbolized as F. Frequencies are measured in standard units called hertz, abbreviated Hz. You learned that in our studies of waves on strings and sound waves. The speed of an electromagnetic wave is symbolized as c, and it's a big number, 3 times 10 to the 8th meters per second. The same equation for an electromagnetic wave, otherwise called light, is the same one that you used for string waves and sound waves. Lambda times f, lambda being the wavelength, f being the frequency, equals the speed of the wave, in this case c. As an example, suppose the oscillation frequency of some electric charge is 6 times 10 to the 14th hertz. The wavelength, according to this equation, is c divided by f. c, 3 times 10 to the 8th divided by the frequency. And we get 5 times 10 to the negative 7 meters. Isn't that something? Well, I'll convert that to 10 to the negative 9 meters for a reason I'll explain in a moment, by adding 2 zeros after the 5. Well, 10 to the negative 9 of a meter is a billionth of a meter, otherwise called a nanometer, nm. 1 nanometer is 1 times 10 to the negative 9 meters. You'll recall that when we studied sound waves, there was a phenomenon known as the Doppler effect for sound. We're now talking about a Doppler effect for light, or for electromagnetic waves. It's a different equation, and it's easier to use than the one for sound. I show the eye of an observer. I show a source of light. The source of light is broadcasting a pure frequency, F subscript S, frequency of the source. The observer eye observes or sees a frequency of F subscript O. O for observer. Now, let's call the relative speed between these two entities, observer and source, V. So, relative to the observer, the source might be moving at so many meters per second to the right or to the left. Well, here's the equation, bottom line. To calculate the observed frequency, what this eye sees, multiply the source frequency by that parentheses. The only complicating factor is there's a positive or negative sign that you have to choose. That's your biggest challenge, really. Well, there are rules, 2 of them. If the two entities, observer and source, are approaching each other, getting closer to each other as time passes, then choose the positive sign. That's analogous to a person on the street corner watching an ambulance race toward her. The two entities are getting closer and closer and closer together. They're approaching. And so the rule is use a positive sign. Otherwise, if the two things are getting farther and farther apart, that is to say, if they're receding from each other, use a negative sign. Well, let's work a simple problem. There is a galaxy moving away from Earth at a speed of 3/10 the speed of light. Its broadcast frequency is 8 times 10 to the 18th hertz. That's the source frequency. What is the observed frequency? Well, this is the equation. It's very simple to put to use. F sub O is the desired quantity. It's F sub S, which is 8 10 to the 18, times that parentheses with a negative sign chosen. Final result, 5.6 times 10 to the 18th hertz. In our next video lecture in part O, I'll be discussing the mixture of light waves, the mixture of colors of light.